Today on The Future of Everything, the future of materials. So much of our technical innovation is fueled by the discovery and creation of new materials. Batteries require special materials that can conduct and store electricity. Integrated circuits must have these little tiny wires that connect the components. Solar cells, kind of a miracle, absorb light and turn it into electricity. And then electronic materials in general are required that can be sculpted, folded, that can function under high temperature, magnetism, humidity, pressure, all of these constraints. So how many useful materials are there? Do we have libraries of materials that are organized by their features and indexed with some kind of Dewey Decimal System? If I need a new material, if I'm an engineer building something, where do I look? I think all materials can be characterized based on the theoretical principles of physics and chemistry, but there's also an experimental component. When you take these materials as they exist and as they're available, how do they perform? Do they have to be absolutely pure, or can there be some impurities? How long will the material serve before it, for some reason or another, stops working? How expensive is it? How available is it? Can it be repaired? These are all critical questions that an engineer has to think about when they're designing an object or a device. Well, Professor Evan Reed is a professor of material science and engineering at Stanford University. Evan, how often are we seeing entirely new materials versus tweaking the old ones by just changing the formula a little bit?
That's a great question, Russ. And the answer is it's actually quite rare. The vast majority of what companies do when they want to make better batteries, for example, or better solar cells, is really kind of engineering the properties of known candidates that have been known for many decades. And in fact, most of the kind of curriculum that you learn as a materials engineer is really geared towards engineering properties of known materials, trying to tweak their properties rather than coming up with completely new candidates for these various applications.
But I take it that some new options would be useful. Are the current capabilities hindering innovation in some ways?
That's also a great question, and it's one that my speculation is probably, but the answer is really not known. And the reason is that there are something like 100,000 or a few 100,000 known characterized materials that have a crystalline structure. And for a typical application like batteries, there may be only just a handful of different materials that are actually used for the cathodes, and all the engineering work goes into those handful. Whether there are any magic materials that are fantastically better than what we're using within that 100,000 or a few 100,000 is really an unsolved problem. We don't know.
So let's step back. For people who don't think about materials every day, could you give us a definition of when you're a material scientist, what is in play for materials? Like, should I think about them as pure substances, or should I think about them as compound substances? Take us through a little bit of how to understand what a material means to you.
Yeah, so for the most part, most properties of materials that we're interested in originate at what we call the atomic scale. So if you give me a set of atoms, particular atom types, and you tell me what the arrangements are between those atoms, I can predict, using, as you said in your intro, some principles of physics and chemistry. I can predict what some of the properties of that material will be. Now, there are additional fine-tuning steps that you can do beyond just the basic atomic structure of materials. You can add impurities. You can also introduce.
So you might add an impurity on purpose, just to pause there a minute. An impurity could help in some way.
Absolutely. Impurities are the addition of a small concentration of a different type of atom that can change the properties of the material in some way that we desire.
So you're talking about atomic level. Should I think of these as relatively, what's the word, homogeneous? Because I know that sometimes they talk about layered materials. Are those in bounds for the kinds of things that you think about?
Yeah, in the realm of materials, we tend to think mostly about a pure material. So, one material, one particular atomic structure, one particular amount of impurities. Um, but in practice, if you want to make a real device,
Hmm.
one material is never enough. You always have some kind of interface with some other material,
Yeah.
even if it's something as simple as packaging. If you make a chip, semiconductor chip, you've got to put some kind of packaging around it to protect it from the environment. And so in practice, things are really, multiple materials, and furthermore, we care about what happens at the interface between those multiple materials.
Right, because we all, even on a household level, we know that certain metals, when they're next to each other, lead to badness, corrosion, all kinds of things. I can't remember which ones they are, but I remember I have to check when I'm doing my plumbing to make sure that I don't put like a brass next to a whatever. Forgive my profound
Sure, yeah,
lack of
absolutely, yeah.
materials knowledge. This is the future of everything. I'm Russ Altman. I'm speaking with Professor Evan Reed about materials. Now, I wanted to get to kind of the fun part, which is you've started to look at using the modern tools of computer science, machine learning, which is a little bit surprising because I think of this as a very physical kind of foundry. And so tell me what the opportunity is for machine learning in material science.
Yeah, first let me give some context. So for the past 50 years or so, the prediction of materials properties has been, at least at the atomic scale, has been accomplished by doing calculations, basically working out the consequences of quantum mechanical types of equations for the electrons, how the electrons behave in a material. And so this is really a physics-based approach to predicting properties of materials, and that's gotten us a very long way. So that can tell us things, for example, like the color of emission of an LED, for example. It can tell us something about absorption of light that we care about in solar cells, or mechanical properties like the elasticity of a material. All
So the
those things.
computation, the physics-based computation has reached quite a good level of precision, it sounds like.
It's reached a useful level of precision,
Yeah.
and it is continuing to improve. So for some properties, it's actually very good, and for others, we're still working on it. So there's still a lot of innovation happening in that space. But that's sort of the traditional approach. And one of the challenges with this kind of approach is that it computationally is very expensive. And so, for example, just anecdotally, typically when we do calculations like this, it can take days or weeks to run on a supercomputer just to predict properties like the color
The
of
LED
an
will be
LED.
red.
Exactly. It takes us weeks to determine that.
I'm only laughing, but I have a profound respect for that capability, of course.
It's a real issue, and if we want to find, the particular magic wavelength we're looking for within this, 100,000 candidates, you can do the math. Take it a week times 100,000, and you're going to be waiting a long time. And so, so what's new is, within the last, say, 10 years or so, are a completely different kind of approach, which you alluded to, which is the use of data. So, after many decades of accumulating data in the literature on properties, for example, of semiconductors that can tell us what the emission wavelength is, we can take all that data, we go to the literature, we try to pull out all these numbers. This particular material emits at this particular color. We pull all that out, we put it into some kind of a database, and then we also know some physical principles. So we have some intuition for how, for example, the atomic structure of material leads to emission at a particular color. So we have a little bit of intuition for kind of what that relationship is.
Without having to do the big expensive calculation, you might be able to ballpark it.
Exactly. So we have, yeah, exactly. So we have some kind of heuristic intuition for, if you have this particular type of atom, for example, it's more likely to emit in this particular color range, so things like that. So these are more heuristics. And so, and then we try to combine this data with these kind of simple chemical or physical heuristics, put them together using tools that we get from data science, which is sometimes people call it machine learning or artificial intelligence, and has a bunch of different names. To lowest order, it's all essentially the same thing. And we try to put this together and use these models that we construct to predict properties of materials. And importantly, as you pointed out, Russ, the key is that these models are very fast to evaluate. It is possible with these models to actually screen through hundreds of thousands and actually millions and potentially billions of candidate materials.
Okay. Which is totally prohibitive in the physics-based modeling that you might otherwise prefer. I'm not even sure you would. Would you otherwise prefer the physics-based, or are there benefits to this approach that even with the computational power to do a full physics, you might still go this route?
That's another great question, and it's something that, naively, my answer is that the physics-based approach is probably better. But in some cases, that might not be true. We don't know. That's an open question, and it's something that my group and others are working on. Which is really better.
Would it be because the physical equations are still to some degree approximations, and so whereas the data might be experimentally measured and be quite precise, the physics might be lagging behind that precision? Is that the kind of reason that might emerge?
That's exactly right. So the data comes from experiments usually, and the experiments are done on materials that have gone through real processing techniques. And they have all kinds of details, like impurities, for example, that are not well characterized. They're not well measured, and so frequently the experimenters don't even know that they're in that material. And so when we make predictions based on that experimental data, it's not inconceivable that we could actually have those predictions better than if we calculated them from some kind of physics principles where we assume that there's no impurities, it's a perfect material. And so sometimes there's a disconnect between the physics-based models and experiments for that reason.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Professor Evan Reed. We're talking about materials, and we're just getting into this idea of data science as a tool for material science. So how far has this kind of work gotten, the kind of new way of looking at the data?
Yeah, so there are, I think the metric of success here would be to come back to what you were talking about at the beginning of the show, would be to point to a material for something that we care about, like a new battery material for your phone or something that really came out of this approach, that all the experts said, well, that's not going to work, or we never would have thought of that. That's sort of the metric for success.
Right, because then even your detractors and your pessimists have to admit that you've made a contribution that might not have otherwise been made.
Exactly. Or we got lucky, random,
right.
We got something like that. But that's really, I think, what it needs. And so far that hasn't happened yet, to the best of my knowledge. But it usually takes quite a bit of time to go from the predictions through synthesis, trying to actually make the materials that we predict and then put them into applications. That process usually takes a period of 10 years or more, sometimes 20.
Right.
So I think we're sort of working through that phase now. There are lots of predictions out there. They're being tested in the lab. So some of our predictions, we work with groups that are actually trying to grow some of the materials we predict and actually test them. And there are certainly promising signs, but so far we don't have that magic, that magic example.
Yeah, so I want to do a little deep dive because I know it's not proven yet, but there was a little bit of excitement about one of the papers that your group wrote about potentially discovering some new battery-related materials. So can you take us through what that story was and where it is, and what is the proof of the pudding that would put the most skeptical people to rest?
Sure. So this is an example of applying these kind of data-centric methods to identifying the electrolyte that goes into a battery. And particularly, we were looking for solid materials that can serve as an electrolyte. So the electrolyte, just for your listeners, is the material that basically allows atoms, the lithium ions, to shuttle between the anode and the cathode. So as you discharge your battery, as you use the battery, these lithium atoms are basically diffusing through the electrolyte to get from the anode to the cathode.
I believe that in grammar school, did I use an apple as an electrolyte or something like. I remember putting electrodes into a piece of food or fruit and having some battery action. But
Okay.
forgive me, it was a long time ago.
Yeah,
but
yeah.
yes, but it's the stuff that separates the positive and the negative terminals of even of a normal battery.
Exactly.
Yeah.
And it determines, for example, the power output. It's one of the things that determines the power output of the battery, which is something we really care about for electric vehicles and maybe potentially electric aircraft someday. So it's a real rate limiting or capability limiting material in a battery. And so we were trying to come up with find new materials, basically look through 100,000 candidates to look for new materials. And we use this kind of data-centric approach. But in addition to this data-centric approach, historically, when scientists have searched for better materials, like a better electrolyte, they tend to focus, just because we're all human, we tend to focus on one property. Like I want to find a material that has the best possible rate at which these lithium atoms can go through this electrolyte, so I get the most power out of my battery.
Right.
And you can do this exercise. You can certainly find materials that are really fantastic in one quantity. But historically, what usually happens is you find those materials, but then they wind up being deficient in some other category that we really care about. Like there's certain constraints on the electrical conductivity of the material. We want that to be very small. And so what we found is that, if you're looking for materials and you kind of look for them one property at a time, it's a really slow and inefficient process. And this is part of the reason why it takes decades to really come up with new kinds of materials for applications. And so as part of this exercise, we were able to develop these models, because they're fast, for a variety of properties of the electrolyte that you care about. So not just the rate at which ions can move through the electrolyte, but these other properties like electrical conductivity.
Right, so you can simultaneously look at all these things that might matter. Even though some of them matter more, they all matter, and you can actually probably even program that in.
Exactly. And this is important because some of these properties are what we call anti-correlated, which means that you can have a lot of one, but that means you pay a price for another one, or you can have the other one, but you sort of pay a price for the original thing. And so what we're really looking for are outliers, kind of rare materials that lie off the kind of the usual distribution of materials. And so looking for these outliers in a sort of serial fashion by optimizing each property one by one is extremely inefficient. So we want to incorporate all these constraints in one approach. And with this data science approach, we were able to do that because these models are fast. We can develop a model for each thing and screen many materials. And
this is the future. Let me interrupt. This is the future of everything. I'm Russ Altman, and we will have more with Professor Evan Reed about what they discovered about batteries using data science next on SiriusXM. Welcome back to the future of everything. I'm Russ Altman. I'm speaking with Evan Reed about materials, and I just interrupted him before we went to the break on this issue of what happened, Evan, when you did this data science looking for surprising materials that might make good electrolytes in batteries.
Yeah, so we developed these data science techniques to identify good electrolytes for batteries, and in the process of running these models, there were certain sets of materials that kept popping up. And these are materials that contain boron and sulfur. And they're really obscure materials. These are things that people studied decades ago in completely different contexts. They weren't thinking about batteries at all. But these are materials that were synthesized and then characterized and put in the literature decades ago. And we pulled them out, and the model was predicting them to be good. And so we investigated a little bit further using some of these physics-based techniques, which we have a little more experience with. We know when to believe them, and how much to believe them. And the physics-based techniques were also predicting them to be very good. And in fact, some of these materials are predicted to be better ion conductors than the best known materials that are currently being studied for the case of lithium-ion batteries.
Right, so that gets people's attention, is my guess.
Right, and so this translates directly into power output of batteries. So there are real applications for this. And so now we're in the process. We're working with a company and also some academic groups to synthesize these materials. And the synthesis actually turns out to be, for a lot of these materials we're finding, it's fairly challenging. It really takes people with deep expertise in synthesis to make them in the way that we need to be made. And so you can see that there's real value in being able to screen through huge numbers of materials so we can really focus those detailed efforts.
If I may, I just have to ask, how old was the literature that you refer to, that where you found these things? And can you tell me just briefly, what were they looking at them for back then?
That's a great question. And so the literature is about 30 years old. And what were they looking for? I don't know. And there's a lot of materials like that in the literature. It's just,
so this was kind of curiosity driven materials research.
That's right. And they were being studied largely for there's a lot of materials in literature that are just, we made this, here's the structure, here's some properties, end of story.
But so I love this because it's a great example of this curiosity driven. That's the phrase that we use for when a professor or some scientist does something out of curiosity. There's a lot of people who say, why aren't you doing useful things? Like, why don't you focus on a specific problem that we know needs to be solved? But the stories like this, and I recognize it's not a complete story yet, but even already, this justifies why scientists need to have a certain percent of their effort just be curiosity driven, because they do good work, they put it in the literature, and then 30 years later, this guy from Stanford, for an entirely now practical reason, is very interested in these materials. So I just want to highlight that because it's a great example where you don't always need to know why you're doing something.
Absolutely, yeah.
So I was interested, you said that a company and others are helping you kind of validate the actual properties. So I presume they're going to synthesize it. They're going to make some test batteries or something and make sure that all of these properties that came out in both the prediction and in the physics stand up. But it raises the issue of, are you a lone island of this data science approach? And what are the prospects for getting it out into the world? Typically, this involves industrial pickup because, as a researcher, you have a limited ability to scale up. So what is the kind of landscape of the future for these approaches?
Yeah, so that's a great question. So what we found to be the real rate limiting step for the adaptation of these kinds of techniques and the deployment of them is really in the data. And so what we've been doing is, there are students in the group who go to the literature, they read the literature, they pull out numbers.
The boss told me to read this 30-year-old
exactly
paper.
Yeah, and that's a very it's a time-consuming process. There's there's human errors associated with it, and sometimes things don't get translated into the paper quite properly, and so there's presumably errors there. It's a very it's sort of an archaic process. And really what would be enabling are, curated, very carefully curated, organized, and managed databases of materials properties, where we know all the details, how they were synthesized, all the details that we think could impact their properties. And this is something that's really it's on a scale that is really bigger than any single academic research group. This is something that really requires kind of the level of investment, kind of a national level of investment to create the infrastructure, not only to organize this database, but also to kind of generate the data, create incentives for researchers to contribute to the database. There's a social engineering challenge.
Right, because I'm sure there's intellectual property issues and you don't want to give away the farm.
Absolutely. And so you need to have some kind of incentive for, it takes effort to put your information in this database. There needs to be some kind of incentive
Is the
to do that.
patent, speaking about intellectual property, is the patent literature a big source of this kind of data that you're looking for, or is it more the published academic literature?
In our case, it's more the published academic literature. And there are attempts to go through the patent literature because it is, it's all online. They try to pull out, certain types of information. But for us, for materials properties, it's really mostly in the academic literature.
Now it seems to me that this kind of effort would also be a matter of competitive advantage in the marketplace. So are you imagining that this should be a national or an international effort or both? Is this something that nations would compete on? How do you imagine the optimal way to set this up?
It could be either. I think, it's at a scale that's bigger than any individual institution. It should be at least a national level effort. And you can certainly make arguments for this. If I have a startup company and we're starting up, we just have 3 people, we have a minimal budget, and our technology company really relies on, our success or failure in our startup is really determined by what materials we choose.
Mm-hmm.
We don't have the budget, the resources to do all this stuff.
Right.
But gee, if there was some kind of national infrastructure where we could go to and we could look up properties and materials, that would be a real advantage for startups, basically companies that don't have, companies that are not the sort of Apples of the world that have
Yes.
multi-billion-dollar research budgets.
And then as you point out, though, you would have to create the incentives for ongoing maintenance. I mean, I always tell my students, it's easy to set up a database for the first time, but many databases die because they don't have like a business plan for maintenance and updating on a regular basis. And so you really have to get the community to say, we have to avoid the tragedy of the commons. I'm going to contribute to this database because I know that not only will I benefit, but others will benefit. And I've done the calculation and it's worth participating. Are people showing signs of that kind of attitude, or do you think you have a lot of salesmanship still left?
I think we've got a ways to go. There are certainly experiments in this area. Some funding agencies are requiring authors to publish all their data with a journal article, for example. Sometimes that's complied with, and sometimes I'm not so sure. And there are other attempts. Certainly you can put up a website, but getting people to contribute is really a key challenge. It's a social engineering challenge, and I don't think that's quite been solved yet.
Well, it sounds very promising. Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.